yesterday I was doing heat and mass transport.
Also, the thing is rolling.
I know.
Alright.
Today, I've invaded reaction engineering. And tomorrow, I will have complete, total, that's redundant, total chemi domination. See?
Don't go past this line.
Got it. See, I've even changed my marker color to black, like my heart. Well, in any case, hey, say, did we do the opening before?
Yeah, but last time when we did this video, I had the camera flipped the other way.
Damn it, that's right. Okay, so yeah, we've already done this, but we'll do it again. Maybe it'll be better. So, today we're doing reaction thermodynamics, which is sort of a prerequisite for talking about kinetics, because chemistry is a lot like a road trip. You don't know how long it will take until you know where you're going. So how we start this off is we do a rice table. Some people call it an ice table. I call it a rice table because without the reaction, you kind of have nothing. So it's a rice table. The first thing you do is you got to get your initial amounts, which you can, if you're in a pinch, just make up numbers like I'm going to do for this example. You can use the ideal gas law of the gas phase reaction to find out what you start out with. Or more likely, you'll probably just be given numbers. And just before anyone wonders what this equation is doing here, this is going to be something for later. So hold that thought. So let's just say we start out with 1 mole of hydrogen and 1 mole of oxygen gas. Obviously there's no water. So the change just basically says, we start out with this much, we're going to lose some of our reactants, gain some of our products. So these are minus signs, that's a plus sign. And to quantify how much we convert, we make this symbol called the extent reaction. There are many ways to do it. I like drawing mine like an E going into a Y. But basically it's the amount of moles of something that gets reacted divided by the stoichiometric coefficient. So how I like to think of it is it's more like how many times did we run the reaction. So in this case we just multiply the stoichiometric coefficient by the extent reaction, like so, and we get our change. In fact, if you notice, when we get to equilibrium is just at some time how much we have left. So we can just write it as this, just the change, the initial minus the change. If you notice, all we've done is just rearrange this equation to solve for n of t. So we do that for all of these, like so. Hooray, we solved the rice table. We're not done there yet because we still don't know how much we've actually reacted. So what we have to do is we have to do sorry, that's bad. We have to do, I did it again, but fine, I guess it stays. We have to use the equilibrium constant, which basically says, it's a way to measure how far we've gone in equilibrium. So if it's greater than 1, we have more products. If it's less than 1, we have more reactants. So how it's written, if you remember thermodynamics, is we just do the ratio of the activities raised to their stoichiometric coefficients, like that. So what we do now is we can substitute the activities, because we learned in thermodynamics that the activity is just equal to the mole fraction in the gas phase, since this is a gas phase reaction, times the fugacity coefficient times the pressure of the system divided by an initial pressure, all of that raised to the exponent, the stoichiometric coefficient. So I'm just going to do that for the other ones and then keep going. And you know what we should put in these videos? Background music. Of course, anything that I pick would probably be too old school, so.
You always put background music now.
No, it's just a thought. Obviously, I don't want you to just start doing it in the middle of a video. So in any case, so now we have a K value fully written out. Now, since I'm just going to say this reaction takes place at atmospheric pressure, that's one, and that's one, because P naught is just 1 bar. It's defined as 1 bar, which is more or less an atmosphere. In this class, we deal with ideal systems, so these are all 1, 2. And so we simplify to this, which is just the mole fractions that were part of the activities. So now we have mole fractions and we have moles in equilibrium. So the way we kept from here to here is just, well, write out the mole fractions using the extensive reactions. So for water, it's just 2 times the extent of reaction divided by the total moles. So I'll just write
Do you have your transport textbook with you?
it should be in my book bag. If I don't, well, oh well. It's just the total here. So that cancels with that. So it's 2 minus extent of reaction, which makes sense because we initially started out with 2, and if you just look at these extensive reactions, you gain 2 every time you use up 3 molecules. So there, that's that mole fraction. The next mole fraction, we'll say it's hydrogen. And that's just,
Oh man, I don't think it's here.
oh well, I guess you have to do it now. Just take my notebook.
No, it's fine. I have my notes and I have my ebook.
Oh, why were you asking for the textbook then?
My card copies more.
Okay, so now we have mole fractions in terms of extent of reaction. So we'll just sub that in here. And so because this isn't a real problem, I'm not going to be able to solve it, but I should be able to set it up well enough so you can see where I'm going with this. Ugh, it's such an ugly extended reaction. 1 minus 2. So pretty much here's the deal. I'm gonna set it all up for you, and you can put whatever number you want for your K value. Because how this normally works is you're given some value, say like, let's say 27, I don't know. And since you have one variable, which you need to solve for, and one equation, you can just do root finding or whatever you like algebraically to solve for what your extent of reaction is. In order to find your composition, you just plug what you find there into here, and then you're done with the problem. So now that we're done with one reaction, let's add a second, which is the formation of peroxide. So this is actually going to change a lot of what we do, so I'm just going to erase all of this because, well, I'll erase it up to here because it's going to change. It's actually going to change a lot of what we do. So let's just do a rice table for this. Now, since we have 2 different reactions, we have to have 2 different extensive reactions. We start with the same amounts because pretty much what we've done is we're putting it in a pot or a beaker or whatever you want. and we have H2 and O2 just in there, and then that's going to react to form some H2O and H2O2. So since they're all in the same pot, we have to consider how much H2 is used up in this reaction for this reaction, and how much we use in this reaction and this reaction. I'll show you what I mean. So this is all the same still, except that we're also using one hydrogen molecule on that reaction, which we have to account for here. So the change also has to include E2 here, which means it's going to include it here. Now, since water's not made in that reaction, nothing changes there. And you'll find that nothing changes here either. So basically, since we're using the same reactants, the oxygen and hydrogen equations of both reactions are going to be the same. Okay, so now we have there. Okay, so now what we're going to do is we can set up two equilibrium values. So we'll have K1 is equal to this here. So, you know, I'm going to write a 1 there. And then we have to do a K2 here, which is just activity of there's no square there. Oh, no, I did that right. Phew, almost made a mistake on live video. That would be terrible. So now that we have these two expressions, you can just simplify them like what we did with when there was just one K equation. So just like A is equal to YI. If you guess the coefficient I, P over P naught. And the one thing you need to be aware of here is when you're making a mole fraction, the total moles accounts for the moles of hydrogen at equilibrium, oxygen, water, and peroxide. So your total amount of moles is actually going to be 1, 2, so I've got water, hydrogen, oxygen, and peroxide is just that. There. Sorry, the notation's just a little sloppy. I want sloppy notation, right? Okay. And so what you get is 1, 2. That cancels that. That cancels that. Minus 2. And so you get that your total moles, yeah, that's right, that makes sense, it decreases by, oh boy, that. Yeah, I think that, yeah, that's right, okay, because the only thing that's changed is that we're making 1 mole here, but we're using up 2 more here. So we should have -1 extended reaction here. Although everything else should be the same, you just have 2 equations and 2 unknowns, so you can do algebra in order to solve them. Well, I think this went better the second time, Dave.
Yep, are you done?
Yeah, I think I'm done now.